This session is static detection and automatic exploitation of intent message, intent message vulnerabilities in Android applications with Daniel Galangali. So, thanks very much.
So good afternoon, everyone. My name is Daniel, and today I'm going to talk about vulnerabilities in intent messages in Android application, and later about a tool we developed to automatically detect those applications and try to build exploit for that. So I'm going to give to you a little bit of overview about Android messages and Android components. Then I'm going to talk about how we build this little tool to audit intent traffic. Then I'm going to explain the threat model we are considering in our research. And then, of course, I'm going to describe the analysis, the design and implementation process for the analysis tool, and then, of course, the results. This work was my master thesis for both Polimi and UAC, and I'm currently working for this company in Italy called Buildo, where we give support for startups and development. So, a little bit of information about Android components. So basically, there are Android applications are built up by mainly two components: activities and services. And these two components talk each other by exchanging messages, intent messages. In this figure, the black arrow is, for example, one intent message. Let's say that the main activity wants to delegate some activity to a next activity, can just send the intent message to the other one. Then let's suppose this activity wants to gather some information from the GPS service running in the background. Then you can just send a message and receive a response, for example, with the current phone location. And this can go on and on in the application lifecycle. So basically, intent messages are the fundamental Android message passing element. They are usually asynchronous, but they have this synchronous version, and so they can be sent like for responses. And they also can be used for inter-application communication. So two different applications can talk to each other with this mechanism. And they, of course, can carry extra information, a set of extra information as key values. Just a few more consideration about intent security. Also, components does not declare to be accessed by intent messages can be accessed somehow. For example, if the sender of the intent message obtains root access, it can it sends an intent to this component that didn't declare any intention to be accessed outside the application scope. It can be accessed because the sender had root privileges. Also, there is no intent origin verification mechanism in Android. And these two things together tells us this intents can be spoofed by an attacker to do bad things. There's been a few previous works about Android intercomponent communication intent messages. The first of them is Comdroid, where they basically gave the first taxonomy about all the vulnerability classes that can happen in this scenario. Then other work about data leakage, component spoofing, networks of application to get to do, for example, privileges escalation and those kind of things. And our work focuses its attention to a single app perspective. And we wanted to go a step further to intent spoofing and analyze it in depth. So we started our analysis by having a look at the Android or the intent traffic through applications. So we basically wanted to log somewhere all those traffic and see what was going on. So we instrumented an Android build, and we basically wrote this monkey runner script to just click randomly on the application to stimulate intent messages. So this is one example of the activity manager. Same things apply for services. This method is like the root of the overload chain of Android starting of the command, which is called on the Android framework when an activity needs to be started. And as you can see here, we have the intent message, and we just took this message, just took this intent, serialized it to a text file, and so we could read what was going on there. Basically, we found commands, label, long text, URLs, and also binary such as audio tracks and images. So we started to wonder what can go wrong here and what can we do to attack a vulnerable application and what can be damaged in the application. And so this is the attack model. Basically, we have an attacker that knows the intent content. So it just, by having this knowledge, it just targets a vulnerable component, using it as a bridge to access mainly free local application resources, such as the UI, the server associated to the application, and the database. And of course, the thing is here that the attacker uses the vulnerable component as a bridge to access those resources. Of course, the attacker is as usually an application carrying some malicious code piece, which is shaped as some useful tool, a torch or something. And we need to keep in mind that this application may obtain root privileges. The victim, of course, is the final phone user that the attacker can, for example, deceive or attack by attacking the vulnerable application and using these local or remote resources to be compromised by the attack. I want to show to you three categories of attacks we define in our scenario. First one is UI target. So the definition of this is basically when the information contained in the intent payload flows to the visible context of the application. This, of course, can lead to some phishing scenario or some case in which the user is deceived. And the user won't have any way to distinguish between the content generated by the attack or the content generated in the common navigation flow. Second scenario is databases. So definition again here is when in the application, in the component, in the vulnerable component, there's a connection between the payload extraction of the intent to the local database. And in this case, we have two kinds of attack. First one is classical SQL injection attack. Second one is some sort of logical attack, in which, for example, the attacker can change the local state of the application. Let's think that one component used to change the pin code of the application. An attacker may send this attack changing just some random pin code, and the user won't be able to access the application anymore, for example. Here, since the attacker is exploiting the receiver vulnerability, and the receiver is in the application, and it was coded to deal with whatever is in the application, we can assume that an attacker that this kind of attack will succeed even if the local state of the application is encrypted, because the encryption key, the vulnerable component will know how to open and how to decrypt the information. Third scenario is remote target attacks. Here we have an attack scenario similar to CRFs. This is basically when the intent payload piece is sent to a remote server. And also in this case, the attacker won't need to steal any token. because the receiver application will know how to build up the request and send it to the server. So now the analysis. The formalization we made was to actually describe points in the code connecting the payload extraction of the intent to these vulnerable resources. So when there is a connection between the payload extraction and some framework call, including some strange action, we mark it as vulnerable. So first thing, we have to detect statements in the code in which the intent payload is extracted. Then we have to follow those variables along the code. And then we need to perform some checking whether the path actually encounters dangerous operation or not. And in the end, if there is a report, we need to verify that this path is actually feasible at runtime. So this is the shape of the analyzer. The rectangle on the left with 3 blocks in it is basically the static analysis chain. So we basically transform the Android bytecode into something we can deal with, for example, Gimple in this case. Then we detect entry points, and then we run this static analysis, in this case IFTS, to follow the variable flows. Then we also collect all the if statements in the code, and we try to build a formula describing the constraint that the input string has to have in order to reach the vulnerable statement. So following code paths basically means to track all the assignment where our base variable is on the right-hand side. And of course, if the variable was contained on the right-hand side, we also will want to track what's on the left-hand side. And we also want to track all the method calls, and we want to expand method bodies not to stop at the first method wrapping everything. And basically, we are using this data structure having the variable, the link to the original variable, which is the variable to which the intent payload was first assigned, then the method in which this variable was declared, and then the statement list. So all the statements containing that variable. Dealing with code flows basically means that, as challenges, basically means that we have to care about all the aliases and all the variables referring to the same information piece. We need to deal with all the transformation and premature ending of the paths. And of course, we need to somehow collect and interpret all the checks that are performed on the variable. So after we have all this information, testing if the application has a vulnerability or not just means to match that exists one of the track statements that's also in our vulnerable statement blacklist that we populated. So we have a vulnerable statement set, and we have the collected set. If there's a match, then the application will be vulnerable. But this is not enough because, for example, that single statement couldn't be reached at runtime. So we also want to validate and prove that this path is actually feasible. How we do the validation? We basically extract from the control flow graph a subgraph containing only the instruction part we care about. And then we translate all the constraint and the string manipulation into some formal representation. And then we take this formal representation and we give it to a string solver. And by querying this string solver, if the string solver is actually able to give to us a solution, we say we have an exploit because the string will match all the constraint along the path. If we have no solution, then we say that that path won't be feasible. Just a few more words about the results. We started picking up 64 applications from the Play Store. Actually, 64 is the number we correctly end up analyzing. from any categories, so travel, finance, whatever, varying in size from 8 to 15 activities and 1 to 3 services. What we found was that 26 applications were actually containing at least one vulnerable path. And we noticed that most of this vulnerability was about UIs. The explanation we got about UI, and the reason why we thought UI was like the most common scenario is because, of course, compared to database and network attacks, the UI ones are like limited in complexity. So like people, programmers making this, it's more common to find this kind of errors in the application since the requirement for the attack is more sophisticated. And we also found out that like just a few applications were actually implementing some kind of sanitization for the intent payload inside the application. I just want to give you one example. This is one popular financial tracking application. And this application was exposing this, in this activity, this capability to basically load every URL into the visible context of the application. So we just thought, well, we can just craft a web page and do this kind of click-jacking attack. So we just, since this is a financial tracking application, we said, okay, we will just ask for the user to reinsert all this credit card information, and when the user will click verify this information, of course, will end up in collected in our server. And so I think this is going to be it. Thank you.